All right, for the next part of the lab, procedure B, what we're dealing with here is, from the first part, I know how fast it's going when it shoots off. And so now I'm going to then take this and I'm going to shoot this ball straight up into the air and then back down. And I want to look at, I'm going to predict how high up it's going to go, and then I'm going to measure that. And so one of the key things here is the fact that if I'm shooting it straight up into the air, it starts out at some initial velocity. And having done this experiment enough, I know it's going to be somewhere around 6 meters per second. I'm going to go ahead, for the sake of this one, just assume that that's the actual answer. You're going to get different answers. It's going to vary anywhere from 5.8 or 5.7 up to 6.3 or so. But I'm just going to go with 6 just as a talking point. So initial velocity of 6 meters per second, and it's going to go straight up. It's going to reach some peak, and go back to the tennis ball video. It's going to go up to some peak, stop, and then come back down. And so it's going to come down like this. And so what I want to know is how much time does it take? How much time is this thing in the air? Or actually, how much time does it take to get to the very top? Well, let's go back to the basic definition. I know that acceleration, let's see if I can make it a little bit thicker so it stands out a little bit better. Acceleration, by definition, so I'm going to put another little bar there, that's the by definition, is equal to the change in velocity over change in time. As we've talked about in other videos, the change in time, just how much time it takes to go up. So generally, this is often written as just a t and not delta t. Change in velocity, well, that's my final velocity minus my initial velocity. Change delta is change. It is always final minus initial. So I have final velocity minus initial velocity over time. Just drop in the delta because it's a common practice. If I've got like 5 different periods where different things are happening, then I might get more worked up about it. But this thing is just going up, and that's all I care about, is just this one period. Now, we are dealing with vectors, so I'm going to say up is positive. I could say down is positive too, but I'm just going to make up positive. Now, I know everything except for time. Acceleration. Well, first off, acceleration is downwards. Acceleration is down, so it's negative. In the lab, I specify, I think, 9.796 meters per second squared. Again, I'm not writing my units down because I'm sticking with SI units. I got meters, seconds, kilograms. Those are the big 3 for this course. If I'm sticking with those, then if I'm solving for time, I know it's going to be in seconds. So 9.796 is equal to my final velocity. Well, at the very top, my velocity is 0, minus my initial velocity, which for the sake of this, I'm assuming is 6 meters per second squared, divided by time. Now notice, first off, my initial velocity is positive here. I'm subtracting a positive number, so it's minus 6, because up is positive, because I said so right here. So I end up with negative 9.796 is equal to negative 6 over t. And so the time it takes to reach the top, to go from where I shoot it to the very top, is going to be 6 divided by 9.796. For you purists, I can keep the minus signs in there. The minus signs are going to cancel out. And so then I pull out my handy-dandy calculator. And 6, enter 9.796 divided by, and I get a time of 0.6125 seconds. Now, again, for you purists out there concerned about significant figures, it's not all significant, but I'm going with it anyway. So this is the amount of time it takes for it to go to the very top. Now the question is, how high up does it go? Well, let's go to another Hewitt equation. So this is the way, except I'm going to write it slightly differently. And so I'm going to shift this down so I've got room. It is not an earthquake you are watching. It is just shifting and tilting. All right. So I'm now going to be looking at the equation of free fall. Now, this does require the concept of, if I'm shooting something up into the air, The amount of time it takes to go up is the same amount of time it takes for it to fall back to the same spot. So up and back. So if I know it's going to take 0.6125, right there, 0.6125 seconds to go up, it's going to take 0.6125 seconds to come down. Again, I'm ignoring air resistance or other forces that might be involved. This works only if it's not going too far, so I can assume the acceleration is constant, and it assumes the only force acting on it is the force due to gravity. So, the equation, we used it before. The change in the vertical displacement, that's why I'm using a y for vertical. I don't always do it, but I'm feeling a little bit saucy right now, is equal to 1/2 times acceleration due to gravity, t squared. Very similar to the equation that Hewitt uses. I think he uses d and he drops the vector symbols. But this is how far an object goes. Well, let's think about that. I'm now looking at the object from the peak back down. Well, this is what I'm trying to figure out. I want to know how far does it go up, which is the same as how far does it go down. So that's going to be equal to 1/2 times 9.8 times 0.6125 squared. And again, pull out the handy dandy calculator, and I do 0.5 enter 9.8 times 0.6125 squared times, and I have 1.838. Now the question is, what are the units? Again, I'm sticking with SI units here, and if I'm dealing with SI, again, I've got that's in meters per second squared. So actually that should be 9.796. Let's see how that affects my answer. 9.8 divided by 9.796 times 83. Hey, it still works out. Now, that's in meters per second squared. That's in seconds, and therefore this is going to be meters. Now, 8.835 is about my height. So when I shoot this thing, and that's going to be in the next video, it's just a quick one. This is the math piece of it. When I shoot this thing, there's a certain technique to it, and there are certain mistakes that can be made that seem scary but actually are not that scary, but we'll talk about that in the next video.